using IR polarimetric observations.
Okay, can everyone online hear me? Yes? No? A clap? Good.
Yes.
Okay. So this will be a more problem-centric and data-centric talk about how we can actually use physics to invert coronal vector magnetism. And this is about the long dream of having coronal vector magnetic dreams, which was slightly unbelievable until a couple of hours ago, until Tom actually showed us and confirmed our Cheng's measurements from 25 years ago that we can actually measure the Stokes V and the line of sight component of magnetic fields in the corona. What I'm doing is trying to devise a method that can be a community tool in order to actually convert the spectropolarimetric observations into actual magnetic field measurements. And we'll see how well that went. Okay. One very simple statement that I hear is that, oh, in the infrared, everything is easy. We know how to do it. We can solve coronal magnetic fields and try to infer them using the iron 13 lines. Well, from a purely formal point of view, yes, those lines form in the saturated Hartley regime plus the Zeeman regime. And you need to combine these two diagnostics in order to get a measure of a full vector.
But you still don't get the full vector.
Technically, yes. So I'm gonna get them.
I'm sorry.
So, in the interest of time, I'm not gonna even go more on the instruments and sensitivity because I think Tom showed you a perfect picture of what that is. Hopefully, we measure all 4 Stokes polarization states, and now let's see what we can do. The first thing is that you have 4 measurements, and usually a model atmosphere, if you want to use models, has at least 9 parameters to solve for. That's a problem. The problem is completely degenerate and not well constrained. The first point is that we need to combine multiple observations in order to be able to constrain the problem well enough to resolve our fields of interest. Now, during our trials, we discovered all sorts of nice things. So, for example, Gabe here worked a lot and showed that the 2 iron 13 lines are kind of incompatible to use together because they have the same lambda factors, and then in the most simple terms, you're going to get the division by 0 and everything blows up. Now, we collaborated with some nice people from Sweden that do atomic physics, and we perform very large-scale magnetic cloud calculations for the silicon series, and we try to see if we can avoid the problem that Gabe pointed out. And we found out that the 1079 line doesn't have a perfect lambda factor that can be approximated with the LS coupling. So a large-scale calculation converted the lambda factor from 1.5, which is the common reference, to 1.47. Division by 0 avoided in this case. That's one problem. The second problem is the actual observation geometry. As we keep talking, actually interpreting these types of observations is not really easy. You get an integrated emission along a line of sight, and you have to deal with that. The problem is that the sun doesn't give you a full 3D volume that you can scan and integrate along. So you're going to have to work with what nature offers you. So one assumption that comes through here is that you need to assume a dominating structure along your line of sight that emits. It doesn't need to be in the plane of the sky. It can be anywhere. But your polarization signal needs to come mostly from there. And in numbers, that's about, I would say, above 85% from that one structure. It can be diffused along your line of sight, so it can be broad, but it needs to be coherent. You need to get a coherent state of Stokes vector coming from that, and not have two of them that have different magnetic and thermal geometries. How can we avoid this? Well, it's simple. You make your inversion so that it fails when you can't assume this condition. And another problem that was also raised by Gabe was that if we don't use the iron-13 line pair, we're kind of in severe problems, because then we would need to combine iron with silicon. Combining iron with silicon introduces another parameter in your problem, and that's the abundance, because they will have different abundances and they will have different dynamical abundances based on where you're looking at. And then you have to deal with that, which is something that you really try to avoid. So we're glad that we could avoid Gabe's problem, or else this would not have worked. Now, even after all of this, atomic issues still exist. So for the moment, we have two forward synthesis codes that we can use to synthesize Stokes profiles for the iron-13 lines and the silicon-10 and the silicon-9. What we found out is that those two codes don't really agree between themselves in the more extreme density range when you go to low heights. Now, since I'm not an atomist, my only way is to consult our friend the sun and actually try to measure the line ratios that are density sensible between the iron-13 lines and see what the sun says about it. Are they compatible with code 1? Are they compatible with code 2? My assumption would be 9. And then we're going to have to fix our codes in order to solve this problem. So for this thing, I'm going to... Yes?
They want to know if you're advancing the slides. You just have the one slide, or?
Yep.
Okay.
So
You know how much time you have.
So in this case, I'm going to run an eclipse experiment for the 2024 to measure just this. Just go as close to the limb as possible and measure the integrated line ratios for the iron-13s. Yes, this affects all of those nice density estimates that everyone else is getting, which might not be compatible with reality. So, this being said, I'm going to introduce LEDB. This is called the Coronal Line Emission Database Inversion, and it is an open source package that you can download and access and use now without ever sending me an email. If you need to send me an email, but it's there. And this was supported through NSO and HAO in the last 4 years. And I wrote it as a semi-automated pipeline for the community to use. There will be bugs. There's no... Tom showed the first data where this can be used, and that first data won't get to us probably in the next year. So this is made in the ether with nothing. There will be bugs. Now, what does it do? So we need to look through a full 3D volume, right? We need to integrate for about 10 parameters, which are the positions, temperatures, densities, abundances, magnetic field strengths, magnetic orientations, thermal and non-thermal speed, and so on. So we need to be clever because this calculation is not scalable. So we build a database of what we need of forward calculations, and then we include in the... We get rid of all of the symmetries that we can. We get rid of all of the parameters that we can, that abundance. And then we're going to left to search just through parameters. We need to search for the line of sight position. So in the 3D space that's not seen in the observation. For the most dominant emitting structure, we need to figure out the density, solving the problem I mentioned earlier, and we can get two intrinsic magnetic field orientation angles. So then you can do all of these calculations, write a database that has a couple of tens of million calculations, and then try to match your Stokes observations in 2 lines to this database. CLEDB works with 1 line also, but you're only going to get a line of sight component, not the full vectors. So the steps are like this. You build a database, you pre-process your observation, you get the spectroscopic products out, You get a line of sight magnetic field out either from one line or the other, or by combining the two lines and getting an average of what each line says. And then you use the database to derive the full vector. Now, so what do you get? You get something like this. And the only thing that you should get from these slides is that there's a left and a right version. Similarly to what HMI does in the photosphere, a spectropolarimetric inversion won't give you the full magnetic field. It's still disambiguated, and it can be disambiguated along the azimuth like HMI does. Because we're in the off-limb corona, we frame the problem to be ambiguated along your line of sight instead of the azimuth, because we can clearly see the azimuth in the observation and through the linear polarization. So for each observation set of 8 Stokes vectors, you will get 2 solutions. And at the moment, you're going to have to deal with disambiguating them. Now, this is an old plot, but I didn't have time to make a new one, of a simple simulation that's extremely extended across the line of sight. So we're talking in about maybe 1 solar radius of emission. That's from different structure that keeps getting integrated. So those are 4 loops that just overlap each other. So what we see here is the BX, BY, BZ components from that simulation in the first column. Then 2 solutions from CLEDB, and then a normalized percentage difference. So the keynote here is that after I fixed that BZ issues, which you can see there, which was a problem, instead of canceling out, it was doubling. You do get in all 3 BX, BY, BZ components about 80 to 85 pixels that are less than 15, 20% differences from the ground truth. And that's what those statistics tell you. The other ones are not necessarily a failure of the inversion, are a failure of what contributes along the line of sight, and if that single structure assumption still holds in that pixel or not. Or vaguely holds, because where it doesn't hold at all, those measurements are directly excluded. But where things are at that border where you don't know if you have a single element emitting or multiple, you might still get some residual errors. Yes, Gabe?
I was going to say, it's strange that the BX and BY component have such different distributions. Why would it?
Because the BX would cancel, it's the component along the line of sight, and it cancels out mostly. So you have way stronger BX fields, they just cancel out.
I didn't, yeah, no, okay. So BC and BY.
BC is vertical, BY is horizontal, BX is cuts through your line of sight.
Thank you, that makes sense.
Okay. And pretty much this is the basics of CLEDB. Now, I've been looking at comp and UComp, and we know what our problem is. You have Stokes I, and this is comp. You have Stokes Q, you have some Stokes U in this frame, but there's no way of measuring Stokes V, at least in an easy way. Okay, so I wondered what we could do to actually get something out of such an observation. So instead of having 8 Stokes profiles, we have only 6. And this is the theoretical setup of the problem. If you have the IQUVs, if you look at the so I invented some K factors to get rid of all of the complicated atomics and equilibrium ionization factors, and just put in the equations the important information that we're looking for. Those are the magnetic geometries. And what we see there is that in only IQU, you do have information about both the line of sight orientation and the azimuth. And if you feed 6 IQU profiles to CLEDB, it can fit and find solutions. The problem is that without the additional constraints that Stokes V provides, you would get four geometrical combinations of solutions instead of the 2 that we are expecting. But now if you use the method that Steve, Richard, and HAO developed, and perform a wave tracking method and get the B-plane of sky field from that method, you will see that those solutions are not for equivalent degeneracy. They come in sets of 2 and 2. So you get 2 solutions for an orientation like this, and then 2 solutions for the opposite, like this. Now, what you see from the plane of the sky field is that one of these sets of 2 is more compatible, but one of the 2 is compatible with the plane of the sky field that you recover from there. So you get the full vector solutions, you use the plane of the sky to pre-select the 2 that work better, and then you get a set of 2 degenerate solutions. Now, because we know the geometry, we can deproject the plane of the sky thing and also get the measure of what P is by just multiplying back with the angle. And then we also have a handle on the field strength. We introduce the field strength to the inversion, and we get a set of, and we can get a set of full solutions. So this just shows, I'm not gonna stay more on it. So the field strength here, this should be the B pose. I got the label wrong. Comes from the waves, and then this is a combination of phi B and theta B's that come in. So technically, you get 4 of these, not just 1. But what I want to show here is that you also get the metric of the line of sight position of that most dominating structure, and this is what's missing in pure analytical inversions. You cannot assume that your structure is in the plane of the sky. You have to iterate through the plane of the sky and look at the photo excitation effect and look at the alignment factors that you get, and then those can help you put your structure in a position in that 3D volume that you're integrating from. Again, as long as the main assumption holds. And this is a simple example. Everything here is preliminary. I need to trust data, method, and everything before going out with it. So take everything with a grain of salt. So this is, for example, one of those 2 degenerate solutions, and just project it into a Cartesian plane in Bx, By, Bz from comp, and compared with some extrapolations, which both the polarities and the field strength match the foot points of these fields that are crossing through your line of sight. And this is a more detailed plot of how such things work. Things are not perfect, but there seems to be a general agreement with the general direction of that we expect for such coronal magnetic fields and what we can recover from And now, since we've been talking about this fact, this is and I included this an hour ago. This is a comparison of your linear polarization azimuth scaled properly and the wave phase angle scaled in the same way. You will see that they generally match, with the caveat that in the right, you look at about a very few seconds of integration, while in the left, you look at an hour and a half. So in some places, there are differences, but they do match. Now you can also see that technically the linear polarization expands more. Yeah. The linear polarization expands more in height, but we need to be really careful of how much we can trust that. It depends on how well comp or UComp can do it. But these should be equivalent measurements. If I had more time, I would have taken a 2-hour average of the linear polarization, well, just a 2-hour difference of the linear polarization to properly compare it with the wave phase angle, because we don't measure polarization in the dynamics sequence. But I'm curious to see So there's very few things. I don't know if my cursor is around there. So around here, you see a small inversion in the wave that's kind of died out in the linear polarization, and so on. So there's subtle differences, but I don't know if this comes from the difference in integration times or something else.
There's the bend flip. I mean, there's the flip, the 90-degree. That's going to be different between them, right?
Yeah, the direction on the left should be right because you do see a loop structure in intensity images.
Yeah, and if you had a loop which is going blue-red, and then depending on its angles and its geometry, you could have a situation where it really is not visible in the azimuth in the same way. Because right when it starts to bend over in a way where that convergence is clear, it gets the bend fleck. So if you were to plot the bend fleck, the linear polarization on top of that would help because it would show you where you have bend fleck.
Yeah, I need to change the color scale to have a specific color.
Or put the vectors on it. See that?
But this was just a quick plot showing this how well these things match, and I think they match extremely well.
They're definitely showing a diverging field at the coronal holes for both methods. Both methods.
And now the last one, and again, take this with a grain of salt. This is one set of solutions. So the columns are BX, BY, BZ with a zoom in over one limb for UCOM. And now we'll have to spend enormous time actually validating that everything is okay with the data, everything is okay with the inversion, everything is okay with the forward synthesis tools, and so on. But what I'm trying to say here is that the vector magnetic fields are here, either from the KIST, either from UCOM. We have the method. It's vaguely it's publicly available binding box, and we can start using these things.
Have you started doing some validation, like the very basic validation, I guess, where you take the vector magnetic fields and then I guess you would be able to forward model it and get I, Q, and U back compared to the observations that you used?
I would need to do that using only models, not models and observations. Because extrapolations are extrapolations and they're not compatible with what you actually see there.
You couldn't integrate again and get back what comp should see?
You can,
Okay.
but if we're just pursuing a validation, I would just forward synthesize the model, invert the model, compare the model with the models, apples with apples. But that just validates the method, basically. Then if you try to do model observation validation, then you'll have to properly quantify the difference between the model and the observation. And that's, I don't know what the difference in that will be.
Any left for another question or so?
Do you see again how you're determining where the structure is weighted most in and out of the plane? I didn't quite catch.
So the database has a resolution along the line of sight, and it takes slices, which can be thicker or thinner and so on. So it takes chunks. Now you do that by seeing the alignment that the atoms get. So the farther away from your plane of the sky is, the alignment in those atoms is higher. And you can use this effect when you're looking at one pixel and indeed there's a structure. If you see a higher alignment than what it should be in the plane of the sky, then you know it's that distance away from the plane of the sky. So it's the anisotropic cone that comes from the photosphere and illuminates your atom. And you can measure basically how the inner radius of that, how high that cone is. Basically, it's height. And then if you have the height, you have the plane of the sky position. It's just trigonometric to figure out what the depth along your line of sight is.
Basically, it fits that position along with the other variables. So
Yes.
that could be one factor that contributes to the degeneracy. You can have a, so something can be in front here and it would give, so that, but
That's exactly how we pose the degeneracy. We posed it as a reference to the plane of the sky. It's either in front or behind, and that's the degeneracy. We don't know if it's plus or minus from the plane of the sky.
I was gonna ask, could, the results from the waves, could the places where it does match, could that be an indication that their emission is from a source? That'd be maybe to
Answer this question, but could you stop presenting? Sort of set up. Okay.
we can talk about it after too. I don't know.